Alright, let me talk to you just a little bit in general about the idea of infinitesimal calculations. See, that's probably misleading. I'm really talking about integrations which we set up using some sort of infinitesimal scheme. In some sense, this is just a shorthand for writing down a finite approximating scheme, then taking the limit as the number of approximating region goes to infinity. Lo and behold, you discover, it's a Riemann sum, so it's an integral. But this way of thinking has served me well, so I thought I'd share it with you. For example, pressure, P, is the force per unit area. So if the pressure is variable, right, for different areas, then you want to think of it this way, it's dF dA. But if we basically multiply both sides by dA, we get dF is pressure times dA. And then if I want the net pressure, I just have to integrate the pressure over the area, like this. And so the pressure may be variable, right? In fact, the pressure is linearly dependent on the depth of the water. If you want to get into the details of that, I don't really want to get into the details here, but so you can calculate the force, the net force on a dam from the water pushing against it using this, even though the pressure is variable. It's more pressure at the bottom of the dam than at the top, and so forth. Another place where infinitesimal calculations come up, so that's one example of this notion. There's so many. I'm just listing a few, but work is force times distance, right? We learned that in middle school, perhaps. But the thing is, if you think about it, what about like a spring force, where the force is variable, right? It's harder to stretch the spring the further it stretches out. So the force is variable, so it's like, you stretch a spring over 3 inches. Should you use the force at the start, which was 0, or the force at the end, which is largest? Which force do you use to calculate the work done? Well, if you think about this, right, if you just think about the little bit of work that's done by moving just a little distance dx, whatever object you're thinking about, then the force over that little displacement going from x to x plus dx, say, well, that force is nearly identical. The force isn't really changing much from x to x plus dx because dx is so tiny, right? So then to calculate the net work, I just take the continuous sum, the integral, and voila, that's the net work done by a variable force going from x1 to x2. I guess while I'm at it, let me just take a second. What happens if the force is constant? If f of x is just equal to some constant f naught, then the work done is going to be what? This, pull the constant out, integral dx from x1 to x2, which is just what? F naught times x2 minus x1. And there we go. We're right back to what we said in middle school, force times distance. It's just that this is a special formula in the case that the force is constant. Since middle schoolers, at least in our current stage of human development, society has not yet gotten to the place where they believe that middle schoolers should learn calculus. That may be a view I harbor personally, but it is not popularly held to, so middle schoolers have to learn work as force times distance because they don't know better. They don't know calculus. But there you go. Of course, in Calculus 3, you learn the real definition for work, which is in terms of a force, which is not only variable, it also depends on three-dimensional position, and you can calculate the work done around a curve in three-dimensional space, but we don't yet have the technology to describe that in Calculus 2. The other thing, of course, we've already talked about, is to calculate area of some curvy shape. You can chop it into little dAs that you understand. The dAs we understand, really, rectangles, horizontal or vertical, but you could also chop a circle, for example, into triangular shapes and calculate the area like that. There are other approximating schemes other than rectangles, but usually we stick with rectangles, horizontal or vertical. And then you add them up using the integral, and then volume. So just to recap here, basically you either have dA equal to y top minus y bottom times the dx, or you have dA is the right x minus the left x times dy, right? And then volume, which is what we're about to get into, you chop the volume into little dv's that you understand, right? So there's kind of a couple different things. So either you have dv is like typical cross-sectional area times, say, your dy or whatever. You might say dz if you want to think about 3 dimensions. Or you have dv. The other thing you could do is like, well, let's see here. Let me just say dv. I'll just write it. I don't want to try to explain it right here, so I'll just say in terms of cylindrical shells. One special kind of cross-sectional area is a circle. So if you do like a circle with a little bit of thickness, it's a disk. So in here is disks. You have disks or washers. If you delete things from the middle, that's a washer. And then cylindrical shells. Anyway, if this is mysterious, it's because I'm not giving you enough detail here to understand it. I will soon. So that's our next thing. We're going to talk about these, and I'm just going to stop and start again then. Thanks, guys.